Today we got problem 1489, critical and pseudo-critical edges in MST. So my guess that will be some edges that are in all MSTs, but not sure. Given I waited undirected. Okay, bidirectional. Okay. What cause the MST weight to increase is called a critical edge, and pseudo-critical edge, which can appear. Okay. Okay, that seems like a standard problem. Oh no, that's not good. 200 edges. Ay. Not great. Okay. Nice. I mean, let's say all edges would have the same weight. Well then, and we got a full graph. With like 200 edges. Which is the square root of that, so like 13, it's 12, so 2 to 12, that should work. That should work, I guess. So, whew. Okay, so essentially it needs to appear in all MSTs. Interesting. Oh, what are we returning? Oh, that's the list of them. Okay. I mean, of course, the stupidest approach is to try all edges. And maybe we could make it somehow smarter. Not sure how, but yet. Okay, so for each edge we just need to say that. Okay, so this is list of all possible. My bet is that with these constraints, the thing is that there cannot be that many trees, if you know what I mean. Maybe dynamic programming, if we sort edges and then we say that well, first we should build MST, but I don't want If we don't find again, bro, I just did it yesterday. So we try. If we remove that, we can try. Like these critical edges are easy. Pseudo-critical. Okay, I mean, it's not that terrible. Oh my god, okay, this is disgusting. Okay, so here is how we are doing it. We first find the MST cost, right? And then we run the algorithm. Deletion critical edge is edge that is in all MSTs, right? So we try one by one each edge, and then if we just try on the subset of edges to build MST, right? And if that MST is larger, okay, critical edge. Next, we try force adding that edge, right? Meaning, here is that edge, give me MST with that edge. And if there is an MST with that edge, and then we are done. Right, that's a pseudo-critical edge, and that's the whole thing. That's the whole shtick. So, and it should not be slow, like testing MST is like mlog m because of sorting plus whatever mlog plus some Ackermann irrelevant thing, and we try for all edges, so that's like m squared log m, and this is like 200, so that's like 40,000 times log of this, which is like 8, so 320, that should pass. Okay, we can do that in CPP. Private. Okay, so I need a function which, given, do I want to do it in, not sure if I want to do it in here. I mean, whatever, let's get painful. So of course we need union find. Oh my god, I should have a template for this or something. Parents and sizes. Okay. Like that, and then no, these sizes should be 1, and then parents we initialize with iota. Okay, and then find void unite. And now if their sizes, we append this, we like add the smaller component as a child of the larger component, and that's it. Then we have like int, let's find MST, int n, vector, int, that's some edges, right? I would have to look up how to erase whatever element, but fair enough. So we need some MST. So I guess we do union find of, I mean, edges could be sorted. UF of n, and then for auto e in edges int ans int x y weight find no UF find if x is 1, if they are not in the same component, we add the weight because that's an edge to the MST, and UF unite. Maybe I should simplify this. So this function will return if they unite it, and then what I can do is just if UF unite E0, E1, E2. Okay, so MST is as simple as that. So now we got MST and this. So int MST will be MST and edges, right? And then vector int ans will have, of course, 2 vectors, and then we go through all edges, right? And now I need to force to have an edge. Int index -1. No, int x, int y, int weight. Now what does this mean? Well, v -1 0, otherwise w. Are the weights positive? Weights are positive, so technically I could just do this. But that's okay. And then if x don't equal -1, then UF unite xy. How are the vertices numbered here from 0 to n-1? What this does is that prepares us for the scenario where we want that edge, right? So if MST of I have to still remove that edge. Oh my god, vector if I don't equal j, e push back edges I, edges j. Okay, so now we build the edges, right? And then first we want to run. So if MST of this, and now we don't pass anything, right? So what this means is that we just keep that vertex and make me an MST is over the MST of the original graph, then ans 0 push back I, and now if MST NE edges I0, edges I1, edges I2, and if we include that and it's over MST, right, then ans 0 push is equal to this, then ans 1, we also need that edge, return ans maybe. Okay, didn't work in case 1. Interesting. So all possible MSTs. Maybe like this. Okay, that works. Oh, sheesh. Okay, well, 4 out of 66 is not great. That's not great, my brother. Okay, now I need some empty paper or whatever. Let's see. So 0, 1, 4, 1. 1, 2, what's that? 6, 2, 3, 4, 5. So 1, 2, 4, 1, 0, 2, 4, 1, 2, 3, 4, 4, 3, 4, 4, 2, 3, 5, 4, 2, and 4, 5, 4, 2. So clearly MST here is 1, 2, 10, I guess. So this makes 2 cycles with weights 1 and weights 2 and then joins them with an edge of weight 4 for some reason. Wait. Oh. Okay, that's interesting. So components is this. If comps plus plus, comps minus minus. Okay, and then we do like comps 1 ans, otherwise this. That's great. And let's call this int m is MST, m equals -1 or m over MST. That's weird, because it says -1, so I mean it is -1, so what's up with that, brother? Oh, okay. Okay, so one thing I didn't count is that when we throw out an edge, then I guess, does it have to be a what the hell? 0, 1, 4, 2, 0, 2, 4, 5, 2, 3, 4, 5, 1, 4, 4, 4, 2, 5, 4, 5, and then 4, 5, 4, 2. Oh, okay. good question. I guess you definitely want this edge, you want this edge, and what's the problem? Let's see. Okay, so they say it's 21, which 15, 23, so I agree with that. Maybe 0, 1, 0, 2, 2, 3, 1, 4, 2, 5, 4, 5. So we have a cycle and this thing. So maybe, I mean, I guess I should be. I'm not sorting the edges. I'm so stupid. Auto E1, auto E2, return E1 to E2 to. Oh my god. Am I really so dumb that I'm not sorting the edges? That is ridiculous, man. What the hell? Okay. No, that shouldn't matter. No, that shouldn't matter. Okay, I mean, we can agree that 2 should belong there. And then what they say? 0, 2, 3, 0, 1, 2, 3, 4, 5 belong there. And these two, and that's fair. I mean, that's exactly how it should be. My output is absolute dog water in this. What's up with that? I mean, okay, if I first, okay, so in first they say that because what would happen if I do this? There is 2 extra here, 1 extra here, and then this is broken. Oh my god. That sucks. Okay, I have to eat, but okay. So so let's see, for the 0th edge, if I throw it out, cost will be still 21. Critical edge. Okay. I mean, that is straight up weird. Yeah, I have to sort them because MST counts on that. Ooh, okay, now we are cooked. Okay, the 0th one. Good question. Maybe this won't change anything, of course. E0, E1, E2. Let's call it an edge. Nice. Great. So edges are not sorted. That is amazing. That is awesome, brother. Awesome. Okay. So edges J0, edges J1, edges J2, E. Oh, okay. That's bruh. Oh, okay, that didn't help. That's great. Oh, that sucks. So why is H1 here? You wanna tell me if I throw H1 out, you won't still be able to build it? 2, 4, 5, 5. Okay, let's run it. So if okay, so the first edge, right? MST is 18 because 5, 5 plus 8, that's 18, right? Now let's say that I skip the first edge, right? And how is it possible that it's higher when I skip edge? Oh my days, because now they, oh my god, okay. Okay, I see where the problem is. Problem is that now we shuffled it and indices are not there. So yeah, that's how it is. Edges I3, and so we need to push in the real index. Now it should work great. So many errors because I forgot what assumptions I made. That's crazy. Okay, it's whatever. if x return this. Okay, let's see if I'm not printing anything. Let's submit that balloon from 15 to 30 minutes real quick, and it's way slow. Oh my god, okay. I'm doing something very wrong. Let's see. I mean, technically I could skip this step, and I could put like flags in here, right? And it could be like flags like that, right? And so instead of building the entire sheet, right, we have this index and then flag which tells us what to do with it. So if not flag, then so ans is 0. If not flag, ans plus equals edges I2, and then UF unite edges I0, edges I1, and then components minus minus. And so they're just doing what I did, so whatever. But there is inefficiency in there. Right, and if flag I plus plus, and if oh, okay, let's call it j, I guess. IJ continue, otherwise edges j. I mean, that's a useless access, but whatever. Edges j this, no, edges j this. Okay, probably don't want to skip anything, so -1, and flag should be 1. And then if we do like maybe this is slow, and we can do like vector int, and that, and then here we can do like const to make it not slow. Okay, let's see. Okay, that's better. So I basically have the correct solution, maybe some inefficient constants, but that's about it, I guess. Okay, fair enough. Kruskal's algorithm, or let's do modified kruskal. Let's finish this so I can eat and then go. It takes so much time to do this problem every day. It's ridiculous, bro. Even some of the mediums ones I was struggling. Anyways, okay, so when critical edge is equivalent with an edge which is in all MSTs pseudo-critical edge, non-critical edge in at least one MST. To test if edge is critical, let MST be the MST weight of the graph provided. To test if an edge is critical, we remove it from the graph and try to make the MST. If the graph becomes disconnected or the MST will cost more, it is an uncritical edge. To test if an edge, if the edge is not critical, to test if it is at least pseudo-critical, we at least pseudo-critical, we force it to be in the MST and then compute MST of the graph given that the edge is or given that edge is already picked. If we forced the edge to be in the MST and the found MST's cost is the same as then we found at least one MST which contains that edge, so we add it to the list of non-critical edges. Pseudo-critical edges. Nice. Pseudo. Okay, approach. To find MST, we use Kruskal's algorithm, which sorts the edges and then uses union find to unite the components of the ends of edges, going from the cheapest to the most expensive edge. Now, to avoid resorting the edges every time, we pre-sort them, and then when computing MST with or without a certain edge, we simply pass a flag and an index to the MST function, which when processed, which either skips the edge with the provided index, or first force adds that edge before iterating over them. To handle computing MST for both mentioned cases. O of m squared alpha n it's like m log m plus m c dot mc dot alpha m which is equal to O of m squared c dot alpha n, the number of the edges, and n is the number of the vertices of the graph. This is because we first sort the edges in m log n, and then for each vertex we try to build two MSTs which are computed by iterating over the edges and doing a union operation for at worst all of them, each of which take O of alpha, and if we use path compression and union by rank/size. Time complexity? I think ON, because ONs, since we are not duplicating the edges and we only store the leaders plus sizes of components in union. Find. Okay. Nice. That took 42 minutes. Okay, goodbye.